So today we saw presentations about Chapter 1, and everything in Chapter 1 had in some fashion or another to do with congruency, congruent angles, congruent segments, and then most powerfully congruent triangles. There were a couple places where we used congruency results to prove things. So in our first theorem 121, we proved this really fundamental result that when I have two intersecting lines, the vertically opposite angles are congruent to one another. So in this picture, the angle A and the angle B have the same measure to one another. And the angle C, which we used as part of our proof, we could also say that it has the same measure as this other angle, which is opposite to it. You know, that wasn't part of the argument, but we could have gone there. And this was simply adding up the angle measure and using the fact. So this relied upon this piece of information, that the measure of a straight angle is 180 degrees by definition. So that's an axiom. That's something that we can just sort of take with us that we don't have to prove. And straightness just means that we are forming an angle with 3 points that are collinear. Right? So A, B, C are collinear. And so the measure of that angle is 180. So working with opposite angles is something we'll definitely be doing a lot of. The next two results dealt with isosceles triangles. So for both of these, and these are both kind of subtle, because what we were doing is kind of making an argument that this triangle is congruent to itself, but doing so in a clever fashion. So to prove that when I have two sides of a triangle being congruent, so when I have an isosceles triangle, that I also have two congruent angles, we went from one triangle that we kind of labeled the vertices in a counterclockwise order, and then we did the same triangle, we just labeled the vertices in a different fashion. So we labeled them clockwise instead of counterclockwise. And then when we do that relabeling, we're really interchanging a pair of sides of the triangle that are congruent to one another. And that was the heart of the argument, that we can argue that these two triangles are congruent because they're made up of the first side, I'm going to call it side 1, which would correspond in this triangle to that side, so side 1, an angle in between. And since that angle is angle A in both figures, those angles are congruent to one another. And then the second side, and we make the argument that because the S1s are congruent to one another and the S2s are congruent to one another and the angle in between them are congruent to one another, we have the all-powerful axiomatic SAS congruency criterion that shows us that these two triangles are in fact congruent, that we don't get a different triangle by changing the ordering of the vertices around. But because they're congruent, that also implies that all of their angles that correspond are equal. And so one of these angles corresponds to the angle in the other triangle, which on the one hand look like different angles, but because they're congruent triangles, they're the same angle. And therefore, the angle at B in the left figure and the angle at C on the right figure are congruent because they correspond in these triangles. But on the other hand, these triangles are really just carbon Xerox copies of one another, and therefore the angle at C on the right is congruent to the angle at C on the left, which establishes by transitivity of equality that those two angles are congruent to one another. So these were kind of weird arguments. These are worth sort of pouring back over to look at the details one more time, just to make sure that we kind of get in what sense these two triangles are the same and in what sense we treat them as different. The same thing happens here in the converse, that if I have two equal angles in a triangle, that I also have two equal sides, two congruent sides. And so having a pair of equal angles guarantees a triangle to be isosceles. And the argument is completely analogous to the previous one, except that because we began with the assumption that two angles were the same, instead of running a side angle side argument, we ran an angle side angle argument. Because this angle and this angle we know are congruent. Then we make the argument to show that this one corresponds to that one, this one corresponds to that one. And because the two triangles in the figures on the left and the right are congruent, that also then implies that the corresponding sides are congruent, which shows that this one corresponds to that one is congruent. But since these are the same figure, that implies that it's congruent to that one as well. So same argument, just with a pair of angles instead of a pair of sides. So being isosceles is equivalently having two equal sides or having two equal angles, and that either one of those guarantees the other. And then we have what I think is a really useful result, the angle side inequality. And the way that I like to think about what this says is that it says that bigger sides in a triangle lie opposite to bigger angles. So if, for example, if I want to find the largest side in a triangle, I should look opposite the largest angle in the triangle, which is a hint to how we prove 1.5.3 later on, the statement about hypotenuses in right triangles. And the clever method of proof for this is you take the bigger of the two angles, whichever it is, in this case it was ABC, and then you place a copy of the smaller of the two angles inside of it by constructing a ray starting from B. So we have now this pair of congruent angles. We had enough room to do so because we started with the bigger side, the bigger angle, and we cut it up into a smaller piece. And we construct, because these two angles are the same as one another, an isosceles triangle according to the theorem that we just looked at. So this is isosceles because of 1.2.7. But then because that's an isosceles triangle, dB is equal to dC. Then we plug in the triangle inequality, which is going to be a constant companion for us this semester. And as we talked about before, we use it in kind of these two different ways. The triangle inequality here was a strict inequality, a less than sign, not less than or equal to. And it's less than because D does not lie along the line from A to B. D is not collinear with A and B, and so we get less than, not less than or equal to. But then we're secretly using the triangle inequality again in a different sense on this line here at the bottom, because when we add up AD and DC to get AC, that happens because D, in fact, does lie along the line from A to C. So we're not only using the triangle inequality, we're using kind of the two different things that the triangle inequality guarantees. That for collinear points, the distances actually add up on the nose to give us the distance from A to C. And for non-collinear points that make a triangle that gives the triangle inequality its name, it becomes a less than rather than an equal to. Okay? And so putting that algebra together and replacing in this first line dB with dC, because we've established that they're equal, gives us the result that we're looking for here. So this is a really nifty proof because it uses a couple of different results from prior in the course as its firmament. It uses the isosceles triangle theorem 1.2.7, and it uses the triangle inequality in two ways. So this is a pretty rich proof, even though it looks pretty short. So definitely worth looking back over. Then we saw some counterexamples, how to turn a statement back around into its converse. I'd rather not get lost in the weeds on these because these didn't really teach us any new geometry in a way. I mean, they gave us an opportunity to play around with vertex labeling and quadrilaterals that weren't convex and all kinds of other stuff, but these were a digression. Coming back to the main theme, we proved that the sum of the angles, interior angles in a triangle, add up to 180 degrees. And the way that we did it is to take our original triangle, which in our figure is this right here, ABC, and introduce a parallel line. And by introducing a parallel line and then treating the sides, introduce a line which is parallel to the opposite side of the triangle. So M is a parallel line to L. By introducing that, we now get a bunch of results from the realm of parallel angles. In particular, we have that this pair of angles is congruent. This pair of angles are what are called alternate. The way that I like to think about alternate angles is if I'm driving a little car along this transversal from left to right, then I see this angle passing me on my right. The very next angle that I see passing me on my left is this one up here. Okay, so I look out the right side of the car, I see this angle. And then when I look out the left side of the car, the next angle I see is that one. So that makes them alternate angles along my transversal. And according to our theorem, that means that those two angles are congruent to one another. And so the overall method of this proof is to take all three angles in my triangle and try to locate them close to one another somewhere. And that's what this parallel line method achieves for us, that we end up locating all three of the angles in my triangle as three individual component pieces that total together to give me this straight angle, XAJ, which is 180 degrees in measure. It bears mention that this whole enterprise took this parallel line for granted. If we don't know that such a parallel line exists, or if there are many different ways to draw a parallel line, which there aren't in Euclidean geometry, but without that existence of that parallel line, we might get a different angle sum for a set of angles inside of a triangle. So we really needed that parallel to be there, which is what makes this Euclidean geometry as opposed to other kinds of geometry. So there was the finishing part of that proof. And then finally we looked at Thales' theorem, or what I like to call the Star Trek lemma, which was a proof that inside of a circle, if I have an inscribed angle, so that would be the angle BAC in this diagram, or what was called alpha in the notation. And if I take the central angle, that was the name that I gave in our previous videos to this angle that we see here, BOC, where O is the center of our circle, that the latter has a measure which is twice the former. So the inscribed angle is half the measure of the central angle, or the intercepted arc is what the language in the book says. And so the method of proof here was just to use the diameter of the circle that goes from A through the center at O to cut these angles into two pieces, and then use some results about angle sums of triangles to justify the equality. So we cut angle alpha into two parts S and T. We cut the angle beta into two parts X and Y. We used the fact that we have a bunch of segments that are all congruent. And the reason that they're all congruent, why is BO, CO, and AO, why are those all congruent? Right, because they all go from the center of a circle out to a point on the circumference of the circle. And by definition of a circle, all of those must be congruent. Great. So we ended up with a bunch of isosceles triangles in this process. Well, did we? I guess we did, right? Because then that makes ABO isosceles, ACO isosceles. And we used those isosceles results to discover some equal angles right here using the isosceles triangle theorem, 1.2.6. And so those combined together with the exterior angle in a triangle theorem that guaranteed for us that X is the sum of W and S, and then likewise for Y, T, and W, or Y, T, and U. Combining all those results together allowed us to deduce Thales' theorem. And then the comment that I made at the end that I want to just kind of reiterate here for our recap is that even though this figure makes it look as though AB and AC are congruent to one another, that need not be the case. We could draw an identical sort of analogous figure where we take A and situate it somewhere very different along the circumference of this circle. Whoops. This would be A, then over there. And the result still holds, that Thales' theorem still guarantees that the measure of this angle here at A is half the measure of the intercepted arc, the central angle, measured here at O. So we didn't need ABC to be an isosceles triangle in order to make the rest of this proof work.